What we're going to do today is one of those problem-solving session classes. So I have a whole bunch of problems here that I intend to solve. However, before I go and solve these, do you have any questions about any of the problems that were assigned so far? Because we're going to go over them first. You have?
Yeah.
Okay.
I have number 600.
Okay. So this is determine the Fourier series expansion of the following signal. So this is 2.2 and 6. And the signal here is, I thought we went over this one, didn't we? X6 of t is sum when n goes from minus infinity to plus infinity, minus 1 to the n sigma of t minus t.
No, we already did.
We did this one. If you go to the lectures before, we did this one. I can do it. It's really easy. So let me just sketch it. This is t. This is how this one looks like. For n equals 0, it's delta of t. And this is t, 2t, 3t, minus t, minus 2t, right? So that's how this signal looks like. Right? That's it. Whenever n is odd, you get minus 1. That turns out your delta pulse downstairs. So the period of this signal is what? T0 is equal to 2t. And let me call f0 1 over 2t. That's your fundamental frequency. Now, I can say this x6 of t is going to be equal to a0 plus sum when n goes from 1 to infinity, an cosine 2 pi n f0t plus bn sine 2 pi n f0t. Now tell me, what is a0 in this case? The DC component of this signal. 0. You see that? Half is up, half is down, right? So there is no DC component. So a0 is 0. How about bn's?
0.
Bn's are 0 because this signal is even signal, right? So it is equal to 0 for every n. So the only thing that I need to determine is an. And I can say that an is going to be 1 over period, which is 2t, integral from, let's go from 0 minus to 2t minus delta of t minus delta of t minus t times cosine 2 pi n f0 t dt. And this is an easy one to evaluate, so you get an is 1 over 2t, and then this is 1 minus cosine 2 pi n f0 times t, which when you substitute, this is 1 over 2t, integral 1 minus cosine 2 pi n f0 is 1 over 2t times t. So this is 1 over 2t, 1 minus, here t and t cancels, 2 and 2 cancel, so it's 1 minus cosine. And so your Fourier series here is x6 of t is equal to sum when n goes from 1 through infinity, 1 over 2t, 1 minus cosine and pi times cosine 2 pi n f0 t, where here f0 is 1 over 2t. So that's a beautiful problem for a midterm exam, right? just you know, it's easy. It uses the symmetry, and there's really no integration, so to speak, right? Delta pulses are always nice to go ahead.
A is 2 over t.
Oh, you're right. See, I made a mistake. So it's 2, 2, 2, 2. Right, so 1, this 2 goes. Okay, the next one was this problem x8 of t. So that's x8 of t is cosine 2 pi n f, not n, just f0. 2 pi f0 t. This one is called full wave rectifier. How does the full wave rectifier look like? Well, here's t, and here's the full wave rectifier. Right? So from here to here is 1 over f0, right? That's from here to here, right? If you imagine the cosine, this is the full period of the cosine. Now, what is the period of this one? Period is 1 over 2 f0. Do you see that? This one actually, when you rectify the cosine, you end up with a signal that has a period that's 1/2 of the original period of the cosine, right? The original cosine repeated after these, but this signal, now if you look at it, repeats after 1/2 of the original period. Okay? So now, let's do the Fourier series of this one. X8 of t is going to be equal to a0 plus sum when n goes from 1 to infinity, and again cosine 2 pi and let me call it f x, right? To make sure that it's different. Plus bn sine 2 pi and fx t. What is fx? Fx is your fundamental frequency. What is the value of fx? Fx is equal to 1 over the period. But period is 1 over 2f0. So it's 2f0. Right? So it's twice the frequency of this original sinusoid. Now let's go and talk about the first thing we determine is a0. Can you give me an approximate value of a0? What is it? Ballpark. That's just before we do some calculations. It's around 1/2, right? So let's it is actually 1/2 to something in that range, right? It cannot be outside of that range, right? So let's just determine. So we know, but always do this, right? Ballpark it so that you know what to expect. This way you are able to catch if you make mistakes, right? Because I understand these problems are very much prone to mistakes. Just had an example of that. You know, I made a mistake in the first one, right? So let's just ballpark it. So a0 is 1 over t integral over t x 8 t dt. So I'm going to integrate here from 1 over, this is t over 2, and this is minus t over 2. So what I'm going to say is 1 over t, integral from 0 to t, and then I'm going to say that times 2. Why? Because what kind of symmetry does this function have? Is it odd or even? Even. So what I'm doing is I'm integrating just this part here, right? And then I'm multiplying that by 2. Okay? And I have to divide by period. So what is the value of the function here? It's just cosine 2 pi f0t dt. And then this t, oh sorry, this is t over 2, right? And t, as you see from there, is going to be 1 over 2 f0. Okay, that's the period. So I have here 2 times 1 over t is 1 over 2 f0, integral from 0 to 1 over 4 f0 cosine 2 pi f0 t dt. The integral of the cosine is sine. So this becomes, let me just make sure, this is 4f0 from here times sine of 2 pi f0 t divided by 2 pi f0, and then from 0 to 1 over 4 f0. That's the integration here. So you can see this, there's a lot of things that cancels here, f0 and f0, 4 and 2 pi, so this is 2 over pi, and then sine of 2 pi f0 times 1 over 4 f0. What is the value of this? This is f0 and f0 cancels, pi divided by 2 is pi over 2, sine over pi over 2 is what? Sine pi over 2?
Pi over 2, 9.
1.
1.
Right, so this whole thing is 2 over pi. So that's f0. So when you divide this is 2 over 3, it's 0.6, right? So we are in this range. Right? So I'm comfortable that this result is good. Okay? So that's A0. The second thing is that I need to determine is AN. So let's just go and determine AN. Now, AN is equal to 2 over period, integral over period, x 8 of t times cosine 2 pi n fx t dt. Remember, I have to integrate, I have to do harmonics here that are my fundamental frequencies, right? So, now, I realize my function is even, so I'm going to say 2 times 2 over, the period is what? The period is 1 over 2f0, right? So it's 1 over 2f0. Integral to period over 2. Period over 2 is 1 over 4f0. What's the value of the function? It is cosine 2 pi f0t, and 10 times cosine 2 pi n times 2f0 t dt. Did you follow this? There's some tricks here. Let's just review what I did again. First, the function is even, so I'm integrating only on the right-hand side. And I put here 2. 2 over period. Period is 1 over 2f0. Right? So I placed it here. 0 to period over 4. Right? To period over 2, sorry. So which is 1 over 2f0 divided by 2, which is 1 over 4f0. Then this part here is the value of the function, which is cosine 2 pi f0 t. Then I have to have cosine 2 pi n times the fundamental frequency. Fundamental frequency, look at there, fx is 2 times f0, right? So that's my fundamental frequency, and then I have just 3 value this integral. Go ahead.
1 over 4f. I think we multiply because we are already using the right side.
Yeah, this is your t over 2, right? What is value of t? T is 1 of the fundamental frequency, and the so look at it over there. T is 1 over 2f0. So t over 2 is 1 over 4f0. I would have integrated from minus t over 2 to t over 2, but I put 2 here, and I'm integrating from 0, right? Just the right-hand side. Now, this integral will take a couple of steps, but it's a simple integral. You just have to be careful not to mess up in trig identities. The way how you deal with this, let's just tidy this up. So this is going to be 2 times 2 times 2, 8f0. And this is an integral from 0 to 1 over 4 f0. Cosine of the product is 1/2 cosine of the sum and cosine of the difference. So this is going to be 1/2 cosine of the sum, which is 2 pi 2n plus 1 f0t, right? And then plus cosine of the difference, which is 2 pi 2n minus 1 f0t. And then everything t. Okay? Just expressing the cosine of the product as sum of the cosine of the sum and cosine of the difference. This is the sum, right? You have 2n f0 from here, and then you have 1 f0, so 2n plus 1. And this is the difference, 2n here, and then minus this f0, so 2n minus 1 times f0. Now, these are easy to integrate, so this becomes 4 f0. Integral of the cosine is the sine, 2 pi 2n plus 1 f0 times t over 2 pi n plus 1 f0. And then plus, evaluated from 0 to 1 over 4 f0, plus sine of 2 pi, there's 2n here, right? 2n minus 1 f0 t over 2 pi, there's 2 as well here. So 2 pi 2n plus 1, 2n minus 1 f0, evaluated from 1 over 4 f0, right? So now when you see that when you substitute zeros, both of these go to 0, so let's just worry about the upper one. When I substitute 1 over 4 f0 here, you can see that f0 and f0 cancels. 2 pi over 4 is pi over 2. All right, so this becomes 4. I can actually simplify this a little bit. f0 and f0 cancels everywhere. And then this 4 and 2 cancels. So I have 2 over pi as a common. And then I have here sine of pi over 2 times 2n plus 1 over 2n plus 1. Okay? And then plus sine pi over 2, 2n minus 1 over 2n minus 1. Okay? And this can be simplified even further, kind of use try to use the fact that this is either plus or minus 1. But my suggestion to you is don't do it, right? You're wasting, let's say wasting time, but you're using time on the exam that is used on the trivial thing. This is fine. If you give me n, I can easily determine what the value of an is, right? So that you leave it in this form, right? And now that you have an, then we have x8 of t is equal to dc, which I computed as 2 over pi, right? 2 over pi plus sum when n goes from 1 to infinity, 2 over pi times sine pi over 2, 2n plus 1 over 2n plus 1 plus sine pi over 2 times 2n minus 1 divided by 2n minus 1. And then times cosine 2 pi times n times 2 f0 t. That's the Fourier series for this particular. Okay? I actually skipped one step. What is the step that I skipped? I just didn't realize. Maybe I should put it here. Dn is equal to 0 for every n. Why? Function e. Alright, so I kind of skipped that. I should have put that in here before, Any comments, questions? So how, it's not difficult, right? You just have to use it systematically, don't be impatient, and kind of as you go along, build these checks, you know, look for DC value, look for symmetry, those are your best friends, right? If you can account something, if you can discard computing something on account of symmetry, no chance of making an error, right? All my BNs are correct, right? Because the function doesn't have it, right? So it's all zero. Go ahead.
The final solution, is it necessary to put everything back into the
Into this form?
Exactly.
Yes, yes.
Well, the reason I ask that is because you've already found your A naught and you've already found your A sub n,
Uh-huh.
and by looking at it, you automatically know what it's going to be.
I know, right? But that's what I'm testing, right?
Oh.
Right? You know, so I understand, you know, what you're saying, right? I already get A's and B's, and I know how to plug them in. But this is an exam, so
Okay.
I want you to plug them in.
Okay.
So that's what you're being tested. Okay? All right? Any other? Okay. Anything else from homework or? All right, so I have some other problems. Let's go through them. The key thing of this problem, where I've seen people students make a lot of mistakes, is at the very beginning, very beginning, where you have to realize that the frequency, the fundamental frequency of the rectified waveform is twice that of the carrier, right? Because once you rectify this, your signal repeats at a period that's 1/2 of the original signal, right? That's not true for a halfway rectified. This is a full-way rectified. Sorry. For halfway rectified, that's not true. If you look at a halfway rectified waveform, and I believe that's the very next problem, halfway rectified looks like this. Period of this guy is the same as the period of the original signal, right? So you have here the period is from here to here. So t here is 1/0, where f0 is the period of cosine, right? But here, no. Here it is actually half of that. So that's the big new thing. The rest of it is pretty much standard method of doing the Fourier series. Okay, let me work out some interesting problems. Did you start this one? Okay. Okay, so the first problem says, show that double sideband may be created by multiplying message signal with periodic signal P of t and through appropriate filter. So here's the, I have my M of t message signal here. And what we've learned in theory about double sideband modulation is that, what is it that I place here? I place my carrier, right? And I multiply the signal with the carrier, and I get my double sideband AM. But what the author is saying here is, let's assume that I'm not multiplying with the carrier, but instead I'm multiplying with a signal P of t, where all I know about P of t is that this is periodic. And then I put this filter here, which is a bandpass filter centered around some frequency Fc. And let's show that what I can obtain here is double sideband suppressed carrier signal. Okay, let's see how I do that. Now, when let's say this one is periodic with period t or fundamental frequency 1/t. So, how do I demonstrate this? Well, if P of t is periodic, what is our build this? There you go. I'm building your reflection. So periodic Fourier series. So let me express P of t as A0 plus sum, or let me do it this way actually. I'm going to say it's C0 plus sum of Cn cosine 2 pi n f0t plus some angle phi. What this is our form 2, right? Where I just express my periodic waveform as a whole bunch of cosines that have particular magnitudes and particular phase. This is of course psi n, phi n, and then n goes from 1 to infinity. So that's what it means when I say that the P of t is periodic. So let me then multiply these two and call this signal here z of t. Well, z of t is going to be equal to m of t times p of t. But this is m of t. Instead of p of t, I can put this Fourier series. That is its representation. So C0 plus sum n goes from 1 through infinity Cn cosine 2 pi n f0t plus, I believe I use theta n, so let me just make consistent with my previous ones. Theta n and put here theta n. So that's what I'm doing. When I'm multiplying with periodic signal, I'm actually multiplying everything with the corresponding Fourier series. Now, I can write this as C0 m of t plus sum when n goes from 1 to infinity Cn m of t times cosine 2 pi n f0t plus theta n. Okay? So now, if I look at what the z of f is going to be, which is the Fourier transform of z of t, it is going to be C0 m of f plus sum when n goes from 1 to infinity Cn e to the j theta n, that's the magnitude, divided by 2 m of f plus n f0 plus m of f minus n f0. Okay? So that's the Fourier transform of this signal. So let me plot the magnitude of this, magnitude spectrum of this signal. This is frequency. This is the magnitude. This is, let's say, m of f. And let's just look at z of f here. I have my m of f back multiplied by C0. So there is this guy, C0, m of f. Let's say this is f0 minus f0. So here I have C1 over to m of f minus f0. I should say magnitude here. Or I assume this is a magnitude anyway. And this is C1 m of f plus f0 over 2. Right? So we get another one of these guys here. Right? So what happened when I multiply with this periodic waveform? I get this periodically extended in a frequency domain where around any NF0, I'm going to get the replica of the signal. Now, the catch is this replica is scaled by Cn, right? But that's okay, right? All I can maybe lose some of the power, right? Relative to the ideal case. So if I want to extract everything, let's say I pick my Fc is equal to F0, all I need to do is place a low pass filter here. Sorry, not low pass, band pass filter, and get this component out. Or I can take the component that's twice the frequency or 3 times the frequency or whichever one integer multiple of the fundamental frequency I want to utilize for the modulation, right? This is very much similar to the basic examples that we did. We actually saw sampling as a multiplication between the message signal and the periodic signal. Which was the periodic signal that I was looking at? it was a pulse train, right? It was every t I had a delta pulse. That's also a special case of the periodic signal. But what this teaches me is that I can be a little bit more forgiving. I don't have to sample with pulses. I can just sample with any periodic signal. And the way how some of these modulators are done is by using on and off switch. Let me just spend a little, just to highlight here. You have your message signal, M of t, that you're going to multiply with this signal. This is my P of t. Now what is P of t in this case? It is sum when n goes from minus infinity to plus infinity, pi of t minus capital T over tau, right? Where tau is the width of this thing, and the t is the periodicity at which you repeat this guy. Now, this is 1 and this is 0. So what this does, if you were to draw this, here's how it looks like. Let's say multiplication of the 2. This is your original M of t. But what you do when you multiply with this signal, you turn it on, and you turn it off. Then you turn it on, you turn it off. Turn it on, turn it off, right? So it's very easy to generate double-sided AM, right? You just flip the switch fast enough, and then you let the signal go through, let the signal don't go through, don't go through, right? So this is equivalent as taking the original signal and multiplying that with this train of pulses, not impulses, pulses here. And what that does, it actually repeats the signal in a frequency domain, periodically extends the signal in the frequency domain, and then you pick the one centered around the integer multiple of the fundamental frequency that you want to use for the transmission. Okay? Did you follow? All right. Now the question here is, let me ask you this. If the bandwidth of M of t, so M of f, is identically equal to 0 when f is greater than w, so w is the bandwidth of M of f, what should be t? What constraint I should have on t so that this whole thing works? So t needs to be, let me just do this, t. But I can say something like this, f0 is 1 over t, right? And from that graph over here, you can see that these periodic extensions are centered at integer multiples of f0. So if I look at here, I want to prevent the overlap between these replicas. And what that means is that f0 minus w has to be greater than w. Or f0 needs to be greater than 2w. You see that? So that's when you prevent the overlap between these cycles. So what that means, so I can put the condition f0 minus w needs to be greater or equal than w, or f0 needs to be greater than 2w, or, which is equivalent, t needs to be smaller than 1 over 2w. So this tells you how often do you need to turn this signal on and off. And this we recognize. What is this? Nyquist sampling criterion, right? So it's the same thing. It's exactly the same thing. It's just that now we're relaxed a little bit in terms of what is it that we multiply with. We don't have to multiply with train of impulses. We can actually multiply by any periodic waveform as long as the period of that waveform is smaller than 1 over 2w, where w is the largest frequency in the spectrum of your message signal. You're going to be okay. You can use this to obtain the double sideband suppressed carrier. Okay? Any questions? Go ahead.
If you like something like this, C of F, the magnitude it should be C1/4.
Where? C1/4? Why?
Because this is equal to 1 to infinity if you line the two sides.
No. Look, there's, I can, look, it goes 1 to infinity, but every n gets you 2 of these. Right, I have the one on the left-hand side and one on the right-hand side, right? So this is already taking the half into account. Right? Already taking half into account. So C1/2. Okay. Let me do another problem.
Sir, I have a quick question.
Uh-huh.
I might not be seeing it. You have Fm plus minus n F naught.
Yes.
Should the n be represented on the Z of F graph? Or no?
This?
Yes.
Yeah. There is a, this is C of n plus F naught, and this is C of n minus F naught. And then this is for n equal 1.
Oh.
And for n equal 2, there is one here, and n equal 3, and so on. Right? So there is infinite to many of them. I just drew this for n equals 0 and n equal 1.
Okay.
Right? And then it goes 3 on. Okay. Let's do this problem. Okay, it says, using orthogonality of sine and cosine, it is possible to transmit two different signals simultaneously using the same carrier frequency. The scheme is shown in figure, and it's known as a quadrature amplitude modulation. So QAM is used extensively in digital communication systems. Demonstrate that the scheme works by evaluating signals, along the way. So here's what the problem is proposing. I'm going to take two signals. They are both of the same nature. Let's say first one I'm going to call Mi of t. And I'm going to use this one to modulate cosine 2 pi FCT. Right? So this is a double sideband AM modulation, just like we thought about it originally. So MQ of t is another signal that's different than this one, but it's of the same nature, right? Both of them are band limited. Let's say both of them are voice signals. Now I'm going to use this one to modulate the carrier of the same frequency but a different phase. And I'm going to make these two phases exactly 90 degrees apart. So one of them is cosine, the other one of them is sine. This is what we call quadrature, right? Oscillator or quadrature modulation. And guess what I'm going to do? I'm going to take the first signal and I'm going to add it to the second signal. Right? So this is going to be my signal x QAM of t. And I'm going to send that to the other side. On the other side, I'm going to take the incoming signal, and the upper branch, I'm going to multiply with cosine 2 pi FCT plus some angle. And in a lower branch, I'm going to have sine 2 pi FCT plus the same angle, right? So this is also two carriers in quadrature, but they're at some angle phi offset from the original ones. And after this, I'm going to use my low pass filter. And this is another low pass filter. And this signal here is going to be called y I of t, or I have it y1 of t, and this one here is y2 of t, and along the way this one is called x1 of t, this one is called x2 of t, this is x1, and this is one called z1 of t, and this one is called z2 of t. And the question is, what is x1, what is x2, z1, z2, y1, y2? Let's just go through this and analyze how does this work. Okay? So, first, this is obviously, this part here is the transmitter, this part is the channel, and this is receiver block, right? So you have the full communication system here. So, at the transmitter, we have this x1 of t is obviously mi of t times cosine 2 pi fct. x2 of t is going to be mq of t times sine 2 pi fct. And finally, this x1 is going to be mi of t times cosine 2 pi fct plus mq of t times the sine of 2 pi fct. Now let me ask you this question. If the spectrum of this one is, let's say, between minus w and w, right, because it's a baseband limited signal, and the spectrum of this one, the spectrum of mi of t. So the spectrum of this one is between minus w and w. And the spectrum of this one is minus w and w. Where is the spectrum of this one? Where is the spectral, where does this signal reside? From Fc minus w to Fc plus w, right? So here, F is between Fc minus w and Fc plus w. Why? Because what this does, it translates the baseband to the carrier frequency. Carrier frequency is Fc, the signal is w in the baseband, so your double sideband AM modulation gives you the bandwidth of 2w from Fc minus w to Fc plus w. Okay? Now, how about this one? Same thing. So what happens here? Look what is happening. These two signals are co-spectrum. They're right on the top of each other, right? They share exactly the same spectrum. Do they interfere with each other? Yes, they do. They are on top of it, right? So you have to actually see, we're going to see how you demodulate them so that you can separate them. But they're co-frequency, meaning they're in the same portion of the frequency axis, and they're co-time because they're using the same frequency at the same time, right? So this signal here also is in a domain between Fc minus W to Fc plus W, this signal as well, right? Because you have two signals that are in this band. When you add them together, they're again in the same band. Okay? So let's look at now what happened at the receiver. And let me first work out this branch, first branch. So Z1 of t is going to be your x1 of t times cosine of 2 pi fct plus the angle phi. Right? So what is happening here? This signal is whatever comes this way, which is this signal here, multiplied by the local oscillator, which is cosine 2 pi fct plus phi. Now, if I substitute, you obtain something like this: mi of t times cosine 2 pi fct plus nq of t times sine of 2 pi fct, and then times cosine 2 pi fct plus phi. Okay, nothing really smart. All I did is just substitute what these values are. Okay, so now let me expand on this expression here. So z1 of t is going to be mi of t, and then I have cosine 2 pi fct times cosine 2 pi fct plus phi. This is cosine alpha, cosine beta. I'm going to say this is 1/2 cosine of the sum plus cosine of the difference. So this becomes mi over 2. Cosine of the difference is cosine of phi plus cosine 2 pi times 2 fct plus phi, which is the cosine of the sum. Okay? This is cosine of the difference on mi, right? So this is just the first term. This times this, right? So you have a mi over 2 cosine of the difference plus cosine of the sum. The second one, I have sine times cosine, and the second one becomes nq of t over 2 times sine of minus phi plus sine of 2 pi 2 fct plus phi. Okay? So again, I'm using trig identities. Sine times cosine gives you sine of the difference plus the sine and the sum. Now, after low-pass filtering, what is it that I obtain? This is my signal y1 of t. Let's look at these individually. For any given phi, this is a constant, just cosine of phi, right? So where is the spectrum of mi of t over 2 times cosine phi? It's at the baseband, right, between 0 and W, right? So what does low-pass filter do to this part? It lets it go through, right? So in y1 of t, I'm going to have mi of t divided by 2 times cosine of phi. How about the second part? The second part is a double sideband AM centered at the frequency of 2fc, right? So when you present this to a low-pass filter, what happens? It goes away, right? So that's what's left from the first one. How about the second one? nq of t over 2 times sine of minus phi is also baseband signal, so it goes through. And I'm going to just say minus nq of t divided by 2 times sine of phi. How about the second piece? Gone, right? The low-pass filter eliminates the second piece because it's a double sideband AM centered at the frequency 2fc. So this is the output at the first branch. Now, if you go to the second branch, it's very much the same analysis. I'm just going to write the result here. Z2 of t is going to be mi of t over 2 multiplying sine 2 pi 2 fc t plus f plus phi 1 plus sine of phi, and then nq of t divided, which will have minus cosine 2 pi 2 fct plus phi, and then plus cosine of phi. Okay? So now, that's Z2. Again, I'm using the trig identities, cosine times sine, and then I get two terms, the sine of the sum and sine of the difference and so on. So now y2 of t, let's just do the analysis of this as well. Mi of t times sine 2 pi 2 fct, that's a double sideband am centered at 2 fc. It gets eliminated by the low pass filter. So the only thing that survives from the first term here is mi of t over 2 times sine of phi, right? So I get mi of t divided by 2 times sine phi, and then from the last one you get nq of t divided by 2 times cosine of phi. So that's my signal y2. Now, let's consider ideal cases, meaning phi equal to 0. Oscillators are synchronized. Okay? That's an ideal case. I have the phase difference between the locally generated oscillator and the oscillator of the modulated signal to be 0. Phi is equal to 0. So if phi is equal to 0, what is y1 of t? Cosine of 0, 1, sine of 0, 0. So you get 1/2 mi of t. And what is y2 of t? 1/2 nq of t. So if I manage to synchronize these two, guess what? I'm doubling the capacity of my channel. I'm using exactly the same spectrum to send two signals in power, right? And if I manage to synchronize the oscillators, I'm actually not, they're not interfering with each other, right? And this is used quite a bit, right? Especially in pretty much in all digital modulation schemes. We take our original stream of bits, we separate into two. One of them we use to modulate cosine, the other one of them we use to modulate sine. We call these I and Q components. That's why I call this I and Q. I is in phase, meaning that it modulates the cosine, in phase with cosine. Q is what we call quadrature, the one that modulates the carrier in quadrature, which is the sine. And this way you double the capacity. Now what happens when phi is different than 0? When phi is different than 0, then there is the crosstalk between two branches, right? Part of the nq of t leaks into the first branch, and part of the mi of t leaks into the second branch. And we can, in analog world, we can talk in terms of the distortion or signal to noise ratio, signal to interference ratio. So if phi is different than 0, meaning these two oscillators are not perfectly synchronized, then there will be crosstalk between these two branches. And that may be bad or may be somewhat tolerated depending on how large the phi is. If it's close to 0, then your signal to noise ratio is good. If it's not, then you have a problem to deal with, right? Go ahead.
For Z1 and T, what causes the phi and the sine to be negative?
Here, why is it minus?
Yes, sir.
That's this guy, sine times cosine. Let me just put it here. Sine alpha times cosine beta is equal to 1/2 sine of alpha minus plus beta. Well, yeah, that's this part. Alpha plus beta, and then what? Plus sine of whatever is with cosine. So it's beta minus alpha. Alpha minus beta. So let's test this one. This should be giving me sine alpha cosine beta, right? So if I do this, this is 1/2 sine alpha cosine beta plus cosine alpha sine beta from the first one, and then from the second one I have sine alpha cosine beta minus cosine alpha sine beta. And you can see these two cancel, so this is equal to sine alpha times cosine of beta. Right? So that's my trig identity. Sine alpha cosine beta is 1/2 sine of the sum plus sine of the difference. Now apply this formula to this cosine times this sine. Right? It's going to be sine of the sum, which is this term, and the sine of the difference, 2 pi fct minus 2 pi fct plus phi. So this gives me minus phi. This minus this is minus phi. Right? Just the application of the trig identity.
It's easy to make mistake.
Just like this, right? It's easy to make mistake, but what would be consequence of this mistake? No consequence, right? In the general understanding, because you multiply sine and cosine, you always get sum in the difference, right? So the difference is always going to be something in the basement, because the t is going to be a linear. There may be some angle phi, but sine of phi, either plus or minus, gives me a constant. So that one will always survive, the other one is going to be rejected. So that, and these trig identities, keep them handy, right? They're in your book. They should be on your cheat sheet. If you don't already know them, you kind of always figure them out. It has to be always sum and a difference, and then the question is where is plus, where is minus, and then you work it just like I did here, so to determine what is. Go ahead.
One more question. For z2 of t, you have well, okay, for z1 of t, you reference as like the cosine difference plus cosine of the sum, but for z2 of t, you have negative cosine of the sum and then cosine of the difference of the sum.
Yeah.
I'm just curious why you switched them around now.
Just a different. You have now sine. Look at it again. Sine alpha cosine beta, right? So sine alpha cosine beta. So it's going to be say again? Z2. Z2, yeah. So I'm multiplying with a sine, right? So Z2 is going to be whatever comes here times sine 2 pi fct. So I have sine, cosine times sine, and then sine times sine. Right? So it's just run through the identities. Sine alpha, sine beta is cosine of the difference minus cosine of the sine. Right? That's this is proper. So sine alpha times sine beta is 1/2 cosine of the difference minus cosine of the sum. Right, that's a trig identity. Okay. Let me do another problem. Okay. The next problem, problem number 4, it says frequency multiplier is a nonlinear device. Remember last time we talked about indirect way of modulating FM, and we said you first do narrowband FM, and then you run FM through a frequency multiplier. So how do you implement frequency multiplier? It's a nonlinear device followed by appropriate bandpass filter. So here's an example of a frequency multiplier. I'm going to square the signal and run it through the low pass filter. And here I'm gonna feed x of t. And the question here is, what is y of t? Right? If I want to double the frequency, so this is frequency double. Now, you probably noticed by working on these problems and working them, the ones that I have in the problem book, there are a lot of problems of this nature, right? Where you have some block diagrams of the functional blocks, and you're asked to determine signals along the way. And these problems may look somewhat complicated, especially if the number of blocks is relatively large. But as a matter of fact, they are the simplest problems of them all. Because all you have to do is work systematically. Sometimes you can look at it and get the picture, and as you become more proficient with this, you're going to be able to look at the whole block diagram and understand what it's doing. But even if you don't, what you do is you label the signals and then work along. Right? Just see what happens here, and then you will end up understanding what the whole diagram does. Here, my x of t is a signal that's, it appears here, angle modulated signal, a cosine 2 pi f ct plus beta sine 2 pi fm t. Right, this is an angle modulated signal where the message signal is a pure tone. Is this FM or PM? It can be both, right? You can't tell, because I don't know really what M of t is. If M of t is cosine, then this is FM. If M of t is sine, then this is a PM. All right, but let's work out our math here. So, is this low pass? No, this is band pass. Rather appropriate frequency. So, if I take and square this signal, so z of t is going to be x squared of t, which is a squared times cosine squared 2 pi fct plus beta sine 2 pi fm t. Okay. Now, so z of t can be written as a squared over 2 times cosine of double angle, so it's going to be 2 pi times 2 fct plus 2 beta sine of 2 pi fm t. Okay? And what is missing? Plus 1, right? Plus 1. Right? So that's cosine squared is 1 plus cosine of the double angle divided by 2. So now, what will this band pass filter do? It will be centered around the frequency 2fc, and it will let the signal that this modulated part go through. It will reject the DC signal. Right? So my y of t is going to be a squared over 2 times cosine 2 pi times 2fct plus 2 beta times sine 2 pi fm t. So what has happened as a result of this nonlinearity followed by the bandpass filter is I have doubled the frequency of the carrier. What else have I doubled? What else is being doubled? No, but this you scale this. We don't worry too much about magnitude because you run this through a power amplifier and it adjusts it right as it needs. But one big thing has been doubled. Go ahead.
The modulation.
Data, right? Data. So this used to be beta. Now your beta is too big, right? So let's just sketch this for a little bit. What is the bandwidth of FM modulated signal, or in general FM PM? what did we say the Carson's rule says? 2 times 1 plus beta times W, right? That's the Carson's rule. It tells us how wide is the bandwidth of a signal. In our case here, it's 2 times 1 plus beta times FM. Why? Because our signal has it has a bandwidth of W. There's only one frequency in the spectrum of this message signal. That's the frequency FM. So the W is the same as FM. So let's look at how does Z of t look like in the frequency domain. And I'm just going to draw this one side. So Z of t, or this is just the Z of f, one side. It's going to be centered at a frequency Fc, and it's going to have a bandwidth of, how large is the bandwidth here? It's going to be 2 times 1 plus beta times Fm, right? So that's the occupancy of my signal Z of f, this guy, right? It will be centered around Fc, which is the carrier frequency, and it's going to have the bandwidth, which is 2 times 1 plus beta times the highest frequency in the spectrum of your message signal, which is FM in this case, okay? So that's the footprint of Z of f. Where is the footprint of Y of f? This is f. No, this is Y of f. What has happened? Y of f shifted to 2Fc. You see that? Went to 2Fc. The carrier frequency here is 2Fc. What is the bandwidth of that signal? So the bandwidth here is going to be 2 times 1 plus 2 beta times Fm. Not exactly double, but close to double, right? Right. If you assume that the beta is larger than 1, then this is twice this, but it's not necessarily. Beta is, go ahead.
C of f.
So again?
Then C of f. If you compare with the equation.
Z of f?
Yeah.
Oh, this is x of f, right? Sorry. This is x of f. Sorry, just this signal, right? Not Z of f. Z of f is the same as y of f, just without the BC component. So x of f has a bandwidth of 2 times 1 plus beta Fm. The y of f is now having 1 plus 2 times beta Fm. So that's the way, remember how we generated wideband FM. We start with something that is narrow, and then let's say you do the frequency multiplication, where you actually not only change the carrier frequency, but also increase the bandwidth of your signal. You spread your energy over larger band. Now the question is always, and I keep on saying this, so hold me accountable to this. Why in the world this seems like highly undesirable, right? Why do I want to use ever larger band, right? I want to squeeze my signal in the smallest bandwidth possible, and I owe you an answer to that, right? So at some point we're going to say, why are we doing this? So far there is no argument in favor. Let me just do one more problem real quick. This is the problem 5, and I skipped one, and there's a couple more problems, so they're gonna just be in the notes posted on the web for your exercise at home. But here's the system I have, Fm of t, and I feed this into a block diagram that and here I have a load detector and DC blocker, and this is Y of t. And it says here, demonstrate that this circuit can be used as an FM demodulator. So let me Z1 of t, and here Z2 of t. Right. So it says demonstrate that this circuit can do actually FM demodulation. Right. So my Y of t needs to be proportional to my message signal. Okay. So let's again, another one of the problems of the nature where you have a block diagram. And all you have to do is just be patient and evaluate the signal at various components. So first thing, what does XFM of t look like? This is a general form of an FM modulated signal, so it is A cosine 2 pi FCT plus 2 pi KF, integral from minus infinity to t, m of tau d tau. Alright, so that's my FM modulated signal. If I look at the signal at this point here, how do I call it in my block diagram? I don't call it. Well, I can actually just and see what Z1 of t is. Z1 of t is going to be 1 over tau. That's this gain here. And what I have XFM of t from the upper branch minus XFM of t minus tau. That's what's coming from branch downstairs. Okay? The assumption here is that the tau is small. Now let me ask you this. What is this? Well, if I have a function f of x, right? And what is f of x minus f of x minus h over h for small h? Derivative, right? Remember how we defined the derivative? Limit when h goes to 0, f of h minus. This is a derivative on the right-hand side. But if the function is continuous, it's the same as derivative on the left. So this one here is approximately XFM of t prime. Derivative of this. Okay? So now that I know that, let me evaluate Z1 of t. Z1 of t is d over dt of a times cosine 2 pi fct plus 2 pi kf integral from minus infinity to t m of tau d tau. When I take the derivative here, it's a derivative of what is underneath this integral, so this is going to be a comes as a constant, 2 pi, derivative of the first term is just fc plus 2 pi kf times m of t times sine of 2 pi fct plus 2 pi kf integral from minus infinity to tau m of tau d tau, and there is another minus that I need to, because derivative of the cosine is really minus sine. Right? So derivative of this a comes out, derivative of the cosine is minus sine, and the derivative of whatever is underneath the cosine is equal to this here. So now let me rearrange this a little bit. This is 2a, 2 pi a, 2 pi a, I can even say fc, 1 plus kf over fc, m of t, times sine 2 pi fct plus 2 pi kf, integral from minus infinity to t, m of tau d tau. Now you notice two parts here to this waveform. There is this part here, which is FM modulated. That stays FM modulated, right? It hasn't changed. It was FM modulated before, it's FM modulated now. But if I look at the magnitude here, what can you tell me about the magnitude? Double sideband AM large carrier, right? So this is double sideband AM, double sideband large carrier. Where this part here is what we call A. We used to call A. This is your modulation depth. So now if I feed this into an envelope detector, what do I get? I get the envelope of this signal. What is the envelope of this signal? This is this Z2 of t. It's going to be minus 2 pi A FC 1 plus A m of t, where A is equal to kf over fc. Okay? And now, if I block the dc value here, what do I get? Y of t is going to be minus 2 pi a fc times a m of t. When I bring in what a is back, this becomes minus 2 pi a times kf times m of t, which means proportional to. So this can be used as a demodulator of an FM signal. As a matter of fact, this part here is a differentiator. And how does differentiator look in frequency domain? If I'm differentiating in time domain, what is it that I'm doing in frequency domain? Multiplying by j 2 pi f. So if I were to plot the response, frequency response of this piece, how would it look like? If this is f, and this is age of f, then this guy looks like this, 2 pi f. And you can see that over the frequency of interest, frequency range of interest, it has a response which is a linear function of the instantaneous frequency. And that's our, by definition, our discriminator. So that's, the differentiator is actually the ideal discriminator. Remember, discriminator was a filter whose magnitude response was a linear function of the instantaneous frequency. We introduce it as, let's assume we have a filter with these characteristics. Well, we now find out that differentiator has these characteristics. It's an ideal discriminator. Okay? All right, so any questions on this? So these kind of problems are going to be for the midterm, right? So work the examples here and the ones I gave you for the. I tried to not overlap. These are some of the problems that are in the second section of the, not solved problems. These are the ones that are unsolved. Okay, so that's it for now. Let's take a little bit of a break and then we'll do some more review after the break.